Welcome to this explainer. Today, we're popping the hood on modern AI. We are going to decode the black box, journeying all the way from foundational transformer mechanics right up to the cutting-edge autonomous agents that are basically redefining software engineering as we know it. If you've ever wondered how these models actually scaled up to trillions of parameters, or how they're now reasoning and taking actions in the real world, well, let's dive right in.
We've got a packed roadmap today covering 6 critical pillars. We'll start with the core transformer engine and DeepSeek's sparse MOE to really ground us in the architecture. From there, we'll look at the hardware orchestration of 5D parallelism, shift into how these models actually think using GRPO, see how they act as autonomous agents, and finally, wrap up with how we scale all this to millions of users via efficient production inference.
Section 1. The core transformer engine. Let's start right at the foundation, focusing on literally the single biggest memory bottleneck that holds AI back.
To really grasp modern AI scale, you absolutely have to understand the KV cache problem. See, AI generates text autoregressively, which just means one token at a time. To avoid recalculating the intense math for every single previous word during every single step, the system caches the key and value vectors. It's a clever shortcut, right? But here's the catch. As context windows push past the 128,000 tokens, which is enough to swallow an entire book or a massive codebase, this memory requirement just explodes. We're talking tens of gigabytes of memory consumed for just one single user request.
So how do we fix that? Well, engineers made a brilliant architectural shift from standard multi-head attention to what's called grouped query attention. Instead of every single attention head demanding its own independent memory-hogging key and value matrices, groups of query heads are literally forced to share a single key and value pair. It's a highly efficient compromise that drastically reduces the memory footprint, and the best part is, it doesn't cause a major hit to the model's actual reasoning quality.
Section 2. DeepSeek and sparse MOE. Now let's look at how the DeepSeek architecture took those memory optimizations and fundamentally rewrote the economics of AI.
Take a second to really think about this number. $5.6 million. That is the total pre-training cost for the DeepSeek V3 model. To put that into perspective, comparable frontier models have historically cost upwards of $100 million to train. So achieving an 18 times cost reduction while still maintaining state-of-the-art performance, you don't get that by just tweaking some code. That requires a complete architectural rethink. Their first major breakthrough was multi-head latent attention, or MLA. Instead of just sharing keys and values like we just talked about, MLA compresses the KV cache entirely into a tiny latent vector. Let's look at the math for a 671 billion parameter model. Standard attention demands a whopping 17,000 bytes per token. Grouped query gets that down to 4,500, but MLA, it crushes that number down to just 1,000 bytes. That's a 16x memory savings, which is exactly what unlocks those incredibly long context windows using far fewer GPUs.
The second massive shift here is moving from dense models to a sparse mixture of experts, or MOE. Think about a dense model like hiring an entire hospital staff to treat a paper cut. Every single parameter fires for every single word, which is a huge waste of compute. MOE completely decouples the total knowledge capacity from the active compute. A routing mechanism steps in and ensures that only the highly specialized, relevant expert subnetworks actually wake up and activate for any given token. When we look at DeepSeek V3 specifically, it is a 671 billion parameter behemoth. But thanks to MOE, it only activates 37 billion parameters per token. Here's how it works. A router evaluates 256 specialized experts and picks only the top 8 most relevant ones for each individual word. Crucially, though, they also utilize exactly one shared expert that processes every single token no matter what. That ensures universal grammar and overall context aren't lost while the specialists do their highly targeted work.
Section 3. Training with 5D parallelism. Okay, having an incredibly efficient model on paper is one thing, but how do you physically compute the math for a 671 billion parameter model without melting your servers?
The reality is, you literally cannot fit a model of this size on one GPU. It's impossible. So engineers deploy 5D parallelism, essentially slicing the math across thousands of chips simultaneously. Let's break it down. Data parallelism splits the training batches. Tensor parallelism fractures the massive individual weight matrices across GPUs using ultra-fast connections. Pipeline parallelism chops the model vertically by its layers. Sequence parallelism handles those massive 128K context windows by splitting the actual text sequence itself. And finally, expert parallelism physically distributes all those MOE experts we just talked about across the entire server cluster. It's a massive orchestration feat.
Section 4, Advanced Reasoning and GRPO. Next up, we transition from raw scaling to actual intelligence. How do we teach these massive models to stop, think, and reason?
For a long time, the industry standard to teach reasoning via reinforcement learning has been PPO, or Proximal Policy Optimization. But honestly, PPO is computationally brutal. It requires loading 4 separate massive models into GPU memory all at once. The policy model that's actually making the text, a reference model keeping it grounded, a reward model scoring the answer, and a critic model estimating the baseline reward. As you can guess, this creates an absolute nightmare of a memory bottleneck.
Enter GRPO, or Group Relative Policy Optimization. It elegantly bypasses this entire bottleneck. Instead of running a giant, memory-hungry critic model just to figure out a good baseline score, GRPO takes a different approach. It generates a whole group of responses to a single prompt and simply uses the average score of that group as the baseline. Responses above the average get a positive reward, and those below get penalized. By totally eliminating that critic model, it frees up massive amounts of GPU memory, allowing researchers to train advanced reasoning on much smaller, more affordable clusters.
Section 5. Autonomous AI Agents. So, once a model has the capacity to reason effectively, what's the next logical step? We give it hands to interact with reality. We are currently right in the middle of an incredible inflection point. The models we've been discussing are rapidly evolving from passive chatbots, where you type text in and get text out, into true autonomous systems. These AI agents don't just talk, they are designed to execute complex, multi-step tasks across real-world software environments, doing things like operating your web browser or independently writing and testing code.
And what's driving this transformation? It's powered by the React loop, which is a continuous structured cycle of reasoning, acting, and observing. First, the LLM brain reasons about a user's goal and forms a step-by-step plan. Second, it acts by selecting a tool, say a web browser, and generates a structured API call. Third, it observes the environment's response to that specific action. Finally, it updates its context and loops right back around, deciding its next move until the overarching goal is fully achieved. It's literally an AI interacting with the world.
Section 6. Efficient Production Inference. Finally, we have to ask, how do we actually afford to serve these massive agentic models to millions of users in a live production environment?
The absolute unsung hero of production inference is paged attention. Because we never know exactly how many tokens a user's prompt is going to generate, older systems used to pre-allocate giant, continuous chunks of memory for the KV cache. That resulted in massive fragmentation and just tons of wasted space. Paged attention borrows a brilliant concept directly from operating systems. It divides the KV cache into non-contiguous, fixed-size physical memory blocks and then dynamically allocates that memory strictly on demand. This virtually eliminates memory waste, which drastically increases the number of concurrent users a single GPU can actually serve.
So to pull our modern production pipeline all together, we utilized paged attention to eliminate memory fragmentation. We rely on tensor parallelism to physically split models across GPUs when they just exceed single card limits. And to solve the issue of slow generation speeds, we use speculative decoding. You can think of speculative decoding like a fast junior intern drafting up a document, while a massive, highly accurate manager model quickly reviews and approves multiple words at once. It drastically speeds up the output for the end user.
Knowing how this engine is built from the ground up, from the microscopic memory savings of multi-head latent attention all the way to the massive hardware orchestration of 5D parallelism, you've got to ask yourself, as these architectures evolve from static text predictors into dynamic autonomous reasoning agents, what happens when they start writing the very software you use tomorrow? The revolution we're seeing right now isn't just about models getting bigger. It's about models learning to act on our behalf. Thank you for joining me on this explainer. Keep questioning and keep learning.